Everyone, today we're looking at the idea of electric fields, that region around charge that is basically where the charge wants to feel its force, or where it's going to apply its force on other charges that are around it. It's the vector sum of many forces that a test charge feels in that space. So the test charge, we need to create a sign, and we picked positive as our convention. So anytime we see a charged object, we will bring a positive test charge close and figure out where the field is pointing from those individual charges or lines of charge or sheets of charge or whatever scenarios we come up with. The electric field strength can be calculated by taking the electrostatic force over that test charge. So the units for electric fields are newtons per coulomb. So how strong the field force is divided by the amount of charge that is in that region. And we have some rules for when we draw electric fields. When we draw electric fields, we're trying to visualize that three-dimensional space around the charge. Like masses warped space-time to create gravity, electric fields warp the space around it because of charges in the region. So the first thing is that the fields will start on positive charges. So fields will emanate away from positives and they'll gravitate towards negative charges. Number two, the number of lines in a particular area will tell you how strong the field is. If there are many, many lines around a certain charge, then that charge must be very, very strong. Three, field lines. When you're drawing the field lines, make sure they don't cross.
There's something very important I forgot to tell you.
What?
Don't cross the streams.
Why?
It would be bad.
I'm fuzzy on the whole good-bad thing. What do you mean bad?
Try to imagine all life as you know it stopping instantaneously and every molecule in your body exploding at the speed of light.
Total protonic reversal.
All right, that's bad. Okay. All right, important safety tip. Thanks, Egon. All right, Ray, take the left. Egon, take the right.
We want to make sure that we draw them radially outwards if it's a positive charge or a negative charge like we did in class, but you don't want field lines to cross. Number four, electric fields are perpendicular to the conducting surface, so whatever the surface is, the field line will come out at a 90-degree angle from that object. And number five says there is no electric field inside a conductor. This would allow the charges to move around and we wouldn't be dealing with electrostatics. So we're going to draw a couple examples of electrostatics and the electric fields around those charges to visualize the space around. So this is what we saw in class. We saw that we had a positive point charge, and I bring my positive test charge close to it. What we can do is see that a positive test charge would feel repulsion. So it would feel a push away from that positive charge, and so I know the field must be pointing away from the positive. If I put the test charge up here, the test charge will repel up and to the right. So no matter where the test charge goes, the field is pointing out in all directions. In that picture there with the black dot and the lines you see, I can't really tell if that is a positive charge or a negative charge. All I know is it is a point charge with field pointing towards or away. If it's a negative charge here, then any positive test charge put in that electric field would feel force inwards. The electric field around negative charges is inwards, while the electric field from positive charges is outwards. And we did talk in class too that if I get further from that point source, we would see that electric force diminish and get smaller and smaller. So forces do weaken and fields do weaken with distance. But these are not just two-dimensional fields. These fields are three-dimensional. All directions around the charge would feel repulsion from positives and attraction from negatives because we chose positive to be our test charge. Let's do another example. So this is on that worksheet that we gave in class. You can see I've got two charged lines here. Maybe they're just two charged sheets. I've got one line completely positive and one line completely negative. What we want to do is put a positive test charge in the region and see what it would feel. Well, if I put a positive test charge anywhere along that positive rod, it's going to feel repulsion outwards. So I'm going to represent that with an electric field pointing away. What if I put the test charge over here, next to the negative? Well, that test charge would feel a force inwards towards the negative pole. So I'm going to draw field lines to represent field to the right. What about if I put that charge in the middle? If I put that charge in the middle there, you can see that the negative rod will want to attract it, but that positive rod will repel it. So no matter where I am in the middle of these two plates or rods, I'm going to feel force to the left. So the electric field shows you where positive charges want to move. The fun part is when you put it on the corners. If I put that positive charge on the corners down here, it's going to feel repulsion from the positive, but then it's going to be attracted to the negative. So it does have some fringe effects here where you get field lines to curve and warp around spaces like this. So that's the electric field around two charged plates or two charged lines. Let's look over at that sphere. That sphere is negatively charged. Let's put our test charge near it. The test charge is a positive always, and that test charge would feel attraction towards the sphere, or over here attraction, or here attraction, or there. So anywhere around that charge, the electric field would be pointing inwards. But here's the fun part. Let's put the positive right here in the middle. Let's see what that test charge would feel. Well, it would feel attraction to the top, but also attraction to the bottom, and attraction to the left, and attraction to the right. So actually any direction that that charge would try to move, it would feel attraction to other parts of the sphere. So if you add up all those electric fields in all different directions, the total net electric field here in the center is going to equal 0. There is no electric field inside a shell or a metal shell. So the charges will be all around the outside of a conductor. There'll be no fields that pass through the inside of that sphere, which is good. You put that test charge in there, or any charged object inside that piece of metal, it's not going to feel any pushes or pulls. All the charges are sitting on the outside of the sphere. So inside metals, no electric fields are present whatsoever. Charges would feel no force on the inside. How about two positives? Well, two positives, I can put my test charge here, and I know I'm going to feel repulsion. If I put the test charge on the left side, I feel repulsion. What if I put the test charge right in the middle? Well, right in the middle, the positive to the right is going to repel it on the left, and the left charge is going to repel it to the right, so the test charge feels nothing. So right here in the middle, between 2 point sources of charge, there is no electric field at that middle location. But if I put the charge just slightly up from that midpoint, well, I'm going to feel strong repulsion up and to the left. I'm going to feel strong repulsion up and to the right, so the net repulsion is going to be upwards. And the same thing if I put a test charge down here. That test charge is going to feel a net repulsion downwards from those 2 point sources. So if I start putting positive charge, my test charge, all around these 2 points, this is what you're going to end up seeing. So a field line is going to come out and bend up. A field line is going to come out and bend up. Over here, the field lines are going to warp away. Field lines will warp away. And here's the electric field next to two like charges. So when we said that two like charges repel, here's your reasoning. Two like charges repel not just because they have the same charge, but their fields are pointing outwards in the same direction. Or if these were two negatives, they'd be pointing inwards. So when those two charges get close, their fields sense each other and warp to try and repel each other away. So it's the fields that do the pushing, not the individual charges. Each charge is surrounded by a field, and that's how they feel that force. But right there in that middle of two positives, you can see that you can actually get no repulsion whatsoever. Or if these were two negatives, no attraction whatsoever. So that's what the book's showing you here as you look through it. If you look at picture B with the two black point sources, you can see the field lines are warping and not bending away from each other, but coming towards each other. That tells me that one of these charges must be positive and the other charge must be negative, because that charge would be pushed away from the positive and towards the negative. Away from the positive towards the negative, and the strongest field would be right there in the middle where it's the densest. It gets weaker up here, and if you've looked at any field lines around magnets, this is kind of what a magnet looks like. It's got curving fields from, on a magnet, the north end to the south end. But in charges, we're going to do from a positive to a negative. So when two like charges come together, their fields warp and do the pushing. So in that packet that we had for drawing electric fields out, there was a drawing of saying, draw me the electric fields near two objects very, very close and zoomed in, and draw me the electric fields around those two same charges when you're really, really far away. So what does that mean? Well, I've got, say, a -2 microcoulomb charge and a +6 microcoulomb charge. What I want to do is draw electric field lines that represent the strength of each of those fields. To show that the strengths are proportional, I'll make 2 microcoulombs equal 2 lines of electric field. And I'm going to draw those 2 electric fields inwards since it's a negative charge. The positive charge is 3 times more charge. So in terms of field lines, I'm going to draw 3 times more field lines. So that means I'm going to have 6 field lines coming out of my positive charge. And you can do any ratio that you want. I could have done 1 line coming out of the -2, and that means I'd have 3 lines coming out of the +6. Whatever it is, just make sure your ratios stay the same. So that's what the charges would look like very close to each other. I'd have a positive charge with 6 lines of force pushing away, and I'd have a negative charge with 2 lines of force pulling inwards. So I can see just from my visual that the +6 is stronger because of more field lines. The question then is, what if I zoomed away? If I could zoom away from those 2 charges there, and this was my new range of looking at those charges. If I'm way out here, I'd say that the net charge on those 2 charges that I've surrounded is +4. So that's the -2 microcoulombs plus the 6 microcoulombs. Gives me a net charge of +4. That means that at this dashed line here, at this line of farness, if you want to call it that, I need to have those 2 charges represent just a +4 net charge. Well, +4 net charge means that I have to have 4 field lines pointing away at this boundary that I've created. So how can I do that? Well, I've got 2 field lines pulling inwards on my negative charge, and remember I have 6 field lines going outwards from the +6 charge. What I want to do is connect field lines to show this overall net electric field. Remember, field lines can't cross, so I'll take this first line and connect it to the -2. I'm going to take this second line and connect it to the back of -2, so I've taken care of those 2 field lines that attract from the positive and negative. And now I'm going to take the rest of those field lines and connect them to the outside edge. If you could not see those 2 charges in the middle there, if this was just one gigantic blob, and you said, okay, there's a charged object there, but I don't know what it actually is, I can see that there's 4 lines of field coming out. Those 4 lines must tell me that there must be a +4 charge in the center. Why is it a +4? Because it's made up of these 2 charges here on the left, that -2 and the +6. But I'm so far away I can't distinguish one charge from the other, so my drawing shows me that there is a +4 pulling away, because I had 2 field lines connect in the middle, and I had the other 4 field lines go out forever. So I'd like you to try one of these on your own. The second example here is a +3 microcoulomb and a +6 microcoulomb charge. Use whatever ratio of lines you want. Draw me what the fields would look like very close to the +3 and the +6, and then, like we did before, Draw me what it would look like very far away from the +3 and the +6. So show what those field lines would look like near and far to represent the overall net charge. So like in this example, we've got the positive and negative again. You can see that there's twice as many lines that come out from the +2 charge versus that -1 charge. And all the field lines that are going into the negative charge have emanated from the positive charge, but there's extra field lines left over. So again, if I blocked out these two charges here in the center, and I couldn't tell what was going on in the middle, I can see that the field lines are pointing away. And if I knew the ratio of how many field lines equals how much charge I have, I could tell you that that blob in the middle there must be charged positively. So that's how we want to represent the electric field strength around charges. You take the force that a test charge would feel in that region and figure out the direction that that force is going to point. What we're going to be doing very soon here is calculating the strengths of those electric fields. So let's assume we had some positive charge called Q, and we have that little test charge right here, Q0. Well, right off the bat, I know that Q0 is going to be repelled away. So I know the exact direction that the electric field is going to point. If I want to know the strength of that electric field, I have to know the electrostatic force over that test charge. So the electrostatic force is just Coulomb's law, K, Q, times the test charge, all over, let's say they're an R distance away, so R squared, and I'm going to divide that force all by the test charge. When I do that, what I'm going to eliminate is the test charge. And if I want to know the electric field strength for a point charge, it's going to be KQ over R squared. The KQ over R squared is just the field strength from this positive charge down here. So you can see it doesn't depend on the test charge, it just depends on the charge I'm focusing on. I need the Coulomb constant, I need to know what that charge is, and I need to know how far away from the charge I am. So KQ over R squared gives us our electric field strength for point charges. So today in class we looked at this concept map that had electrostatic equations that we're going to use. We filled in this box here with the electrostatic Coulomb force. If you follow the grid there, I'd like you to fill in where the electric field strength would go. Which of these three bubbles left will give you the electric field strength for a point charge. Go ahead and try and fill that in, and we'll talk about these next time.